Welcome back to 14.3, my friends. Let us finish off the next example. Electricity can be used to decompose molten NaCl into its elements. Molten NaCl, so there's something new to talk about. Molten just means liquid state. Alright, so if I was to melt table salt or sodium chloride, I would melt it into a liquid state where the ions would now be free. This is a topic that would have some issues for us if we were continuing towards the diploma, but we are not, so we're just going to take a look at being able to deal with these cells in molten state. We're not going to look at some of the weird complexities that go with it. So what we want to do is just write the half reactions, draw the labeled diagram, and figure out what was happening at the anode and cathode, much like we did in the previous example. Now we have some starting points here. Okay, so we do have our long positive bar, we have our short negative bar, that makes this electrode here the positive one. Now for this in an electrolytic cell, again, positive represents the anode this time. It's that one subtle change. Negative, there you go, we put that one there, and as we label this, that must be the cathode. So given the information that we have in the battery symbol, we were able to get to anode and cathode. In other times, you might have information about the products to identify reduction and oxidation, and then use that to figure out which is which. To figure out the rest of this one, we should kind of go through our entities method, and our entities will be a little bit different because of the molten state. So, entities here. Alright, all we have is a molten or melted NaCl. So you would have Na plus in a liquid state, and you would have Cl minus in a liquid state. There is no water here whatsoever. Okay, so you've just melted salt. This would be an extremely hot and dangerous system, but we would need this if we wanted to be able to get any of this particular metal here or get our chlorine gas. So that's our only two entities. We can still use our table to figure out OAs and RAs. Chlorine and sodium are both on the table. So take a moment to go through there and find it, and you'll find that you only have one OA and one RA, so therefore they are the strongest of each. This isn't the challenge with this particular problem. So I have my SOA or my OA here, therefore a reduction is what is going to happen to my SOA, and therefore that is also taking place at the cathode, which we identified over here. And so I would have Na plus gaining an electron to form solid sodium. For my oxidation half reaction, that's my SRA, and there's my anode. And so I have from my data table there 2 chlorides giving up 2 electrons to form chlorine gas. All right, so there is some fixing that needs to be done here. We kind of ignored it in the earlier one here because we weren't really worried about coming up with that net reaction, but figured I might as well show it in this second example. And so we can come up with a net redox. And so that'll be 2 Na plus, 2 Cl minus to give me 2 Na and 2 chlorine gas. You might notice that I haven't included the cell potentials for any of this one. Your data booklet is only for ones in 1 molar aqueous solutions. If I have no water, I have no aqueous solution, so therefore I have no cell potentials. If we were to give you a different data table that had the molten cell potentials, then fine, great, we could include them. But you might notice here that from our data booklet, we cannot do this. All right, so we just have our net reaction and the products formed. So reduction at the cathode has solid sodium, so I would expect that my sodium ions in the molten state are gaining that electron to form Na solid on that inert electrode. As for chlorine, you can see that chlorine gas is being produced at the anode. So again, much like before, I'm expecting some bubbling. All right, and all of these bubbles should be chlorine gas. there you go. There's that example from a molten state. Don't let it mess you up. Just understand what the word molten means. It just means that your ionic compound is now melted and liquid, and you will have those ions now freely swimming around in that liquid state. All right, so take a look at the example on page 640. All right, that's just taking a look at what's going on between voltaic and those secondary cells we kind of ignored earlier, but really spontaneous versus recharging for your rechargeable batteries is kind of explained here on 640. Read 639 to 643 for more examples on electrolytic cells. You will be tested and challenged on your quiz to differentiate between what they look like, how they behave, what anode and cathode are, which isn't different, the signs, and so on and so forth. So just be mindful of that one. You will want to practice this. All right, 644 and 645 have lots of good examples that you can certainly look at. Answers again on D2L in the electrochem section. I would also recommend that you go to my videos, not just on YouTube. I'll see if I can't copy those over into another playlist as I continue to get familiar with this. But on D2L right now are a bunch of videos that will show the differentiation between voltaic and electrolytic and how each one works. All right, so you might want to access those if my examples weren't sufficient. You'll notice that there's more notes here, so we should quickly talk about that one. Okay, chloride anomaly is one of those weird specificities that Alberta Ed just likes to throw into their content. I do not want you to look at this at all. Like, oh my God, get rid of it. Yuck, 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 yuck. This will only confuse, pretend it never happened. Chloralkali process, same thing. Never ever look at that. Production of elements, if you wish, you can take a look at this one. This is really just talking about why we needed molten. All right, there's an issue. Water eventually becomes an issue to prevent us getting things like our alkali and alkaline earth metals out of a solution, so therefore we need melted salts. And an example of that one is the production of aluminum, which at one point would have had you a very, very wealthy person. But the moment we figured out how to use electrolysis to get aluminum easily, look at what happened to the price crash. It's almost like oil today. All right, so we have that one. Few other things. Don't worry about these. Great, whatever. If it comes up in future chemistry, knock yourself out. Okay? So all I really want you guys to take from 14.3 is how to draw, identify, and calculate within a electrolytic cell. And there's your practice assignment. So 14.3 is now nicely put to bed. Good luck with your practice. And I will see you for cell stoic in chapter 14.4.